We've seen how we might examine the relationship between a categorical and a quantitative variable by seeing how the summary statistics and shape of the quantitative variable differ with the different values of the categorical variable. In this video, we'll now look at how we might examine the relationship between two categorical variables. Recall that when we refer to the distribution of a variable, we're talking about the pattern of the values in the data for that variable, showing the frequency of occurrence of the values relative to each other. For categorical variables, the distribution is given by the counts or frequencies, or the relative frequencies, of the observations for each of the categories of the variable. In an earlier video, for the anthropology data of measurements on 400 skeletons, we saw the distribution of mass or BMI classification and sex. Now, what if we're interested in looking at these two categorical variables together? Our anthropologist is interested in learning about how the error in age estimation is associated with the body mass index. But it's important to also consider the effect of sex here. If, say, the error in age estimation also differs with sex, it will be important to understand if the body mass index classification differs with sex for these observations. As another of the first steps in understanding these data, we should investigate the joint distribution of body mass index classification and sex so that we can learn things such as, do we have equal numbers of females and males who are obese? Or are there equal numbers of males and females in the underweight category? And so on. We can see the joint distribution of BMI classification and sex in a contingency table, sometimes called a cross-tabulation, or a two-way table since we have two categorical variables here. In the contingency table, we classify our 400 skeletons two ways, by BMI classification and by sex. The table contains the counts or percentages of the number of observed values for males for each of the BMI classifications and for females for each of the BMI classifications. We can see from the table that 46 or 12% approximately of the 400 skeletons are underweight males, 28 or about 7% are underweight females, and so on. For a graphical display of the joint distribution, we can plot the frequencies in either side-by-side or stacked bar plots. I've constructed them so that the height of each bar is the number of skeletons in each body mass classification for each sex. From the side-by-side plot, it is clear that there are many more skeletons in our data that are males with body mass index in the normal range than skeletons in any other category. And for the female skeletons, we can also see that normal weight is also the most common of the BMI classifications. However, by looking at the total counts of the bars for males in the stacked bar plot, it is clear that there are many more males than females in our data. In fact, there are more than twice as many males as females. So although the normal weight bar is taller for males than it is for females, it is difficult to judge from these plots if a greater fraction or proportion of the males tend to be normal weight than the fraction of females who tend to be normal weight. And we need to do some more work to make a fair comparison. The marginal distribution of a categorical variable can be thought of as the distribution of only one of the variables in a contingency table. We can see it in the margins of the table by taking the row or column totals. To understand whether the BMI classification is the same for both sexes, we need the distribution of BMI classification separately for each sex. This is known as a conditional distribution. Given that a skeleton is male, the conditional distribution is the distribution of BMI classification just for males. And similarly, we can look at the conditional distribution of BMI classification for females. The relevant quantity that we need for the conditional distribution, and we can calculate it from the contingency table of counts, is the column percentage. That is the percentage that each count in our contingency table is of the total number of observations in each column, which we can find using the marginal distributions for the column totals. Note that for both males and females, the conditional distribution proportions sum to be 1. Graphically, we can compare the conditional distributions of BMI classification given sex by plotting the column percentages in stacked bar plots. From these plots, we can see that the proportions of underweight and obese skeletons are higher in the females than males, and the proportion of normal weight skeletons is higher for males than females. We say the two variables in a contingency table are independent if the conditional distribution of one variable is the same for all values of the other variable. As we've noted, the distributions of BMI classification seem to differ between males and females, so it seems that BMI classification and sex are not independent for these skeletons. We can also look at the conditional distributions of sex given BMI classification. These are the row percentages, or the proportion each count in the joint distribution is of its row total. We can see that each row in this case sums to be 1. And here, for example, we can see that 62.2% of the underweight skeletons are male. We'll now go to another example, the result of a study to test the efficacy of a new vaccine for HPV. HPV, or human papillomavirus, is a common sexually transmitted infection that can cause genital warts and some types of cancer, most notably cervical cancer. People infected with HPV often do not have any symptoms and thus are unaware that they are at risk of transmitting the virus to others. This results in an environment in which the virus can spread readily. In the US, for example, it is estimated that 20 million people are infected with HPV, and 90% of these people are unaware of their infection. In response to the spread of the disease, vaccines have been developed and are currently being adopted widely. In Toronto, for example, an HPV vaccine is now administered free of charge in school to all girls in grade 8. There are many types of HPV. We'll only look at protection against HPV-16, the most common type that is associated with 55% of all cases of cervical cancer. We'll look at data from the Patricia study, a large study in 2004-05 that recruited over 16,000 women from 15 to 25 years old in 14 countries. The women were randomly assigned to receive either the HPV vaccine or a hepatitis A vaccine in a 3-dose regimen, and were then followed for 3 years to assess their health. In our data, we'll only include the women who received all 3 doses of the vaccine. While there are multiple outcomes we could consider, such as markers for cervical cancer and other consequences of HPV infection, we'll consider simply whether or not a subject contracted a persistent HPV infection in the 3 years of the study. Here are 4 tables that we can construct from the resulting data. Let's look at these 4 tables to see what we can learn. In particular, which numbers indicate whether or not the vaccine seems to prevent infections? The first table is the contingency table of counts, classifying subjects by whether or not they received the HPV vaccine and whether or not they acquired an HPV-16 infection. In this table, we can see that the Patricia study was large, with over 12,000 participating subjects receiving all 3 doses, and with approximately equal numbers, just over 6,000, receiving the HPV vaccine or the other vaccine. Of those who received the HPV vaccine, 23 acquired an HPV-16 infection by the end of the study period, while 345 subjects in the other group acquired an infection. In the joint distribution of proportions, we see that 3% of the subjects acquired an infection, with 2.8% of those in the group who did not receive the HPV vaccine. In the table of row proportions, we see that, of participants who received the HPV vaccine, only 0.4% acquired an infection, while in the group of patients who did not receive the HPV vaccine, 5.7% acquired an infection. And in the table of column proportions, we can learn information such as, of the subjects who acquired infections, 6.2% were in the group that received the HPV vaccine, and 93.8% were in the other group. Because the question of interest is, does the vaccine work at preventing HPV-16 infection? In this case, the row proportions, or the conditional distribution of infection status given whether or not a subject received the HPV vaccine, gives the most direct interpretation. An infection rate of 5.7% versus 0.4% certainly seems to be compelling evidence that the HPV vaccine is effective. In later videos, we'll examine whether a difference this large could have happened just by chance or if it's statistically significant. Let's look at one more example from a report on the findings from a 20-year follow-up of a large-scale study of thyroid and heart disease carried out in England in the mid-1970s. We're showing a subset of the data containing measurements on 1,314 women who were classified at the beginning of the study as current smokers or having never smoked. And we're interested in the 20-year survival status for these women. Looking at the contingency table for these data, the column proportions tell an interesting story. Of the smokers, only 24% had died, but of the non-smokers, 31% had died. Does this study show that smoking might lead to a greater chance of surviving 20 years? Of course, there's a twist here. Let's look at the column proportions for the tables of smoking and survival status broken down by age grouping. Although age is a quantitative variable, it is sometimes given in groups to illustrate a point. As we can see from both the tables of survival by smoking status broken down by age grouping, or from the side-by-side bar chart, for all age groups except the 25 to 34-year-olds, the opposite conclusion is reached. That is, the death rate is higher in the group of smokers than in the group of non-smokers. How did this happen? Age is related to both smoking status and survival. The stacked bar chart shows the age distributions for smokers and non-smokers. The non-smoking population includes more older women. When the study was started, few of the women over age 65 were smokers. But, of course, many of them, since they were at least 65 at the start, had died by the end of the 20-year follow-up period. Moreover, this study could potentially underestimate the harmful effects of smoking, since the observed small percentage of older smokers could have happened because smokers tend not to survive to age 65, so there were fewer smokers in the older age groups to enroll in the study. This is an example of Simpson's paradox, in which conditional distributions within subgroups can give the opposite conclusion to conditional distributions for the combined observations. Age here is a lurking variable. We need to always watch for lurking variables which, if taken into account in our analyses, might affect our conclusions. In some upcoming lectures, we'll talk about data collection and how to design a study to mitigate the effects of lurking variables.